In this video, we discuss learning outcome number 1 for lesson 10.1, which is about defining important terminology related to scatter plots and correlation, including scatterplot, correlation, linear correlation, and linear correlation coefficient. By the end of this video, my hope is that you'll be able to define those terms and that you'll be able to construct a scatter plot and use a scatter plot to subjectively infer whether there's a correlation between two variables. Now, I'm actually not going to show you how to construct a scatter plot in this video. I tend to use Excel to construct my scatter plots. If you want to see how to construct a scatter plot using Excel, you'll want to watch the homework help videos for lesson 10.1. This video is primarily about the important terminology that we're about to discuss and interpreting scatter plots to infer whether there seems to be a correlation between the two variables. To motivate this discussion, let's look at an example. So let's say you have a set of ordered pairs, a bunch of data, and the first element in each of those ordered pairs is a person's waist circumference. And the second element in each of those ordered pairs is the person's arm circumference. If you're interested in answering this question, does there appear to be a relationship between waist circumference and arm circumference? One way that you could answer that question is to graph that set of ordered pairs. The graph of that set of ordered pairs is called a scatter plot or scattered diagram. Typically, we plot the first variable on the x-axis and the second variable on the y-axis. Now, when we say, or when we ask, is there a relationship between the two variables? Another way we could ask that is we could say, is there a correlation between waist circumference and arm circumference? In statistics, the word correlation means that there is a relationship between the two variables. Since we have a distinct pattern of plotted points, so as waist circumference goes up, arm circumference tends to go up too. That suggests that there is a correlation between waist circumference and arm circumference. Now, here are a couple of definitions. Now, correlation is just a relationship between two variables. It doesn't necessarily have to be a linear relationship. A linear correlation suggests that the paired data appear to lie on a straight line. Now, it does not have to be a perfect straight line, but it has to have what seems to be a constant slope as you go from left to right. As one variable increases, the other one increases. Or maybe it's possible that as one variable increases, the other one decreases. So that if one variable increases and the other one increases, and the data appear to lie in a straight line, we would say that that's a positive linear correlation. If one variable increases while the other one decreases, and the data appear to lie on a straight line, we would call that a negative linear correlation. So here's our example with our waist and arm circumference again. We see that there's a linear correlation here. The distinct pattern of the plotted points is lying on a straight line, approximately. They're not all lying on one line, but as we look at this graph from left to right, it seems that as waist circumference goes up, arm circumference goes up, and that slope tends to be approximately constant. Now, here's an example of two variables where there isn't actually a correlation. You see how the data are just everywhere? We have all these dots all over the XY plane. This is a graph of a person's weight and their pulse rate in beats per minute. If this is representative, what this suggests is that there's no correlation between weight and pulse rate. There's no distinct pattern in the plotted points, so it appears that there's no correlation between those two variables. Now, if I look at this one, I see that as we go from left to right, these green dots seem to lie near a straight line. And if we look at the linear correlation coefficient, which we're going to discuss in more detail in the next video, that is this R value. It's a 0.859. That R value that is positive and close to 1 indicates a positive correlation between those two variables. If we have a distinct straight line or linear pattern, we say that there's a positive linear correlation if when the x values increase, the corresponding y values increase. So as we look at the graph from left to right, we see a line with a positive slope. As x goes up, y goes up too. Now this one also appears to have a linear correlation, these two variables x and y. They appear to lie in a straight line, but that line has a negative slope. As x goes up, the y values go down. Notice that the R value associated with this relationship is a negative 0.971. So this is a negative linear correlation between the two variables. Since we have that distinct straight line or linear pattern, we would say that there is a linear correlation. Since the slope of that line is negative, we say that there is a negative linear correlation. As x increases, the corresponding y values decrease. Now this one does not indicate a linear correlation. If I look at this scatter plot, there's definitely a relationship there. Those points seem to lie on a parabola. You see it? It's a parabola facing down. The R value here, which we'll discuss in more detail in the next video, is 0.330. Now this indicates, when I look at this graph, this scatter plot indicates a nonlinear correlation. So we see here that we've got a distinct pattern, and that pattern suggests a relationship between x and y. But since the pattern is not a straight line, we'll say that this is a nonlinear correlation as opposed to a linear correlation. If you're saying to yourself, this feels really subjective, how can we confirm that there is actually a correlation? It turns out that we're going to use hypothesis tests later. While examining scatter plots is subjective, I would still recommend that you do it, because if you do so, you can quickly reveal whether there's a correlation between the two variables. If I graph in it and it looks like there's a line between the variables and I see that that line has a positive slope, I'm expecting a positive linear correlation. If I graph that scatter plot and the points seem to lie around a line with a negative slope, I can say that there's probably a negative linear correlation. Or if I graph my data and it appears that all of my points lie on a parabola, or maybe they lie on what looks like an exponential function or some other type of curve, I might say there is a pattern there, but it's not a linear pattern. It's very easy to construct these scatter plots in Excel, as I'll show you in the homework help videos. So it's absolutely worth your time to just look at the data and see if there seems to be a linear correlation based on that graph, based on that scatter plot. So while this is subjective, and you can say, I think that looks like it's linear, and you and your friend might disagree, this is a very quick way to sort of get you started in the process of analysis. Now, if we want to make it less subjective, if we'd like to make this more concrete, we can determine if there is sufficient evidence of a linear correlation using a hypothesis test. In this case, whenever we're using the hypothesis test, our sample statistic is this linear correlation coefficient R. And the population parameter that we're trying to estimate is called the linear correlation coefficient rho. It looks like a P, but it's actually a lowercase rho from the Greek alphabet. If we want to conduct that type of hypothesis test, we're going to use either the critical value method or the p-value method. So we're going to talk more about the linear correlation coefficient R in the next video. I hope you are comfortable now just looking at graphs or looking at scatter plots and seeing whether there appears to be a linear correlation between two variables, and whether that linear correlation would be positive or negative, or whether there might be a nonlinear correlation between the two variables.